This is SpaceTime, Series 19, Episode 92, for broadcast on the 23rd of December, 2016. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, the new antimatter breakthrough hoping to illuminate some of the mysteries of the Big Bang. The famous red supergiant star Betelgeuse spinning faster than it should. And PanSTARS releases the largest digital sky survey ever undertaken. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Scientists are now a step closer to understanding how the universe came into existence following the first ever optical spectrum measurements of an antimatter atom. A report in the journal Nature claims the study undertaken at CERN, the European Organisation for Nuclear Research, by the Alpha collaboration has allowed physicists to compare normal hydrogen with its antimatter counterpart. Matter and antimatter are oppositely charged versions of the same thing, which will annihilate each other when they come into contact. Science's understanding of the universe through cosmology tells us that equal amounts of matter and antimatter were made in the Big Bang 13.8 billion years ago. Consequently, the universe should have been annihilated out of existence virtually as soon as it formed. Yet, clearly it didn't, and we live in a matter-dominated cosmos. This conundrum is one of the central open questions in fundamental science. And this new study is the first to take scientists down the path of finally understanding why. To do this, researchers looked at hydrogen, the simplest and most common known atom. All atoms consist of electrons orbiting a nucleus. When electrons move from one orbit or energy level to another, they absorb or emit photons at specific wavelengths, forming an atom spectrum. And each element has its own unique spectrum, a kind of atomic fingerprint. It's because of this that spectroscopy has become such an important tool in many areas of physics, astronomy and chemistry. It helps characterize atoms and molecules and their internal states. For example, in astrophysics, analyzing the light spectrum of a remote star allows scientists to determine its composition. The most familiar everyday example of this is the orange light emitted by sodium streetlights. With its single proton and single electron, the hydrogen atom also has its own spectrum, and as the simplest and most abundant atom in the universe, it's well understood by scientists, with a spectrum that's been measured to a very high degree of precision. One specific property of the hydrogen atom known with a high degree of accuracy is the so-called 1s to 2s transition, which has been determined with a precision close to 1 part in 100 trillion. It's the equivalent of knowing the exact distance between, say, Sydney and Canberra to better than 1/1000th of a metre. On the other hand, anti-hydrogen atoms are poorly understood. Because the universe appears to consist entirely of matter, the constituents of an anti-hydrogen atom, the antiprotons and positrons, have to be produced and assembled into atoms before the anti-hydrogen spectrum could be measured. ALPHA's a unique experiment at CERN's antiproton decelerator facility. It's able to produce anti-hydrogen atoms and hold them in a specially designed magnetic trap, manipulating anti-atoms a few at a time. Trapping anti-hydrogen atoms allows them to be studied using lasers and other radiation sources. Now, moving and trapping individual antiprotons, or for that matter individual positrons, is easy because they're charged particles. However, once you combine them to create neutral antihydrogen, things get a lot more complicated and difficult. In fact, the authors had to develop a specially designed magnetic trap that relies on the fact that antihydrogen is still an itsy-bitsy bit magnetic. The antihydrogen is produced by mixing plasmas of about 900,000 antiprotons from the antiproton decelerator with positrons, resulting in the production of about 25,000 antihydrogen atoms for each attempt. The antihydrogen atoms can then be trapped if they're moving slowly enough when they're created. Using a new technique in which the collaboration stacks anti-atoms resulting from 2 successive mixing cycles, it's possible to trap an average of 14 anti-atoms per trial, compared to just 1.2 with earlier methods. Then, by illuminating the trapped atoms with a laser beam at a very precisely tuned frequency, scientists can then observe the interaction of the beam with the internal states of antihydrogen. As I mentioned earlier, the measurement was done by observing the 1s-2s transition. The 2s state in atomic hydrogen is long-lived, leading to a narrow natural line width, so it's particularly suitable for precision measurements. In a research project that's been ongoing for some 30 years involving hundreds of scientists, the Alpha collaboration replaced the positively charged proton nucleus in an ordinary hydrogen atom with its negatively charged antimatter counterpart, the antiproton. They then replaced the hydrogen's normal negatively charged electron with its antimatter counterpart, the positively charged positron. This resulted in the creation of an antihydrogen atom. By shining laser light at a well-defined frequency under antihydrogen atoms held in a trap, the authors were able to achieve the first ever observation of a spectral light in an antihydrogen atom, allowing the light spectrum of matter and antimatter to be compared for the very first time. This experiment has now determined the frequency of the antihydrogen transition to just a few parts in a tenth of a billion. And within the experimental limits, this result shows absolutely no difference compared to the equivalent spectral line in normal hydrogen. It's an important finding because it's consistent with the standard model of particle physics, the theory that best describes particles and the forces at work between them. And the standard model predicts that hydrogen and antihydrogen should have identical spectroscopic characteristics. The Alpha collaboration are now working to further improve the precision of their measurements. You see, measuring the antihydrogen spectrum with high precision offers an extraordinary new tool to test whether matter behaves differently from antimatter, and thus to further test the robustness of the standard model. You're listening to SpaceTime with Stuart Gary. The famous red star Betelgeuse, better known to most people these days as Betelgeuse, is apparently spinning a lot faster than it should, possibly because it's eaten another star. A report in the Journal of the Monthly Notices of the Royal Astronomical Society claims the red supergiant, which is due to explode as a supernova any day now, was probably in a binary stellar system with a companion star. Betelgeuse is the 9th brightest star in the night sky and the 2nd brightest in the constellation Orion after Sirius. If Betelgeuse were located where our Sun is at the centre of our solar system, its surface would extend out past the main asteroid belt between Mars and Jupiter. In fact, the star would wholly engulf the orbits of Mercury, Venus, Earth and Mars. Calculations of its mass range from slightly under 10 to a little bit over 20 times the mass of our Sun. And it's fairly close to the solar system, located just 640 light-years away, down the road in astronomical terms. Because it began its life as a high-mass blue giant and consequently burnt through its nuclear fuel supply fairly quickly, it's less than 10 million years old. Having been ejected from its birthplace in the Orion-OB1 association, which includes all the stars of Orion's belt, Betelgeuse is now moving through the galaxy at a speed of around 30 kilometers per second. As a bloated red supergiant, Betelgeuse is now reaching the end of its life. It's no longer on the main sequence fusing hydrogen into helium in its core. In fact, soon it will attempt ion fusion, at which time the core will collapse, triggering a Type II supernova. Betelgeuse is easy to see in the night sky. It's the bright red star marking the shoulder for Orion the Hunter. The study's lead author, J. Craig Wheeler from the University of Texas in Austin, says for such a well-known star, Betelgeuse is somewhat mysterious. It's already expanded to many times its original size and will someday explode. No one knows exactly when, but it's likely to be sooner rather than later. Wheeler says that means it might happen in 10,000 years from now, or it could be tomorrow night. A new clue to the future of Betelgeuse involves its rotation. When a star inflates to become a supergiant, its rotation should slow down. Like a spinning ice skater bringing her arms in to speed up her rotation and then opening them up again to slow down that spin, so too Betelgeuse's rotation should have slowed as the star expanded. But that wasn't what Wheeler's team found. Instead, they've calculated that Betelgeuse is spinning some 150 times faster than it should. Using computer simulations to model the star's rotation for the first time, the authors speculated that Betelgeuse must have had a companion star when it was first born. They hypothesized the companion star was circling around Betelgeuse in an orbit about the size that Betelgeuse is now. And when Betelgeuse turned into a red giant, it literally consumed the companion star. Once swallowed, the angular momentum of the companion star's orbit would have been transferred to Betelgeuse, speeding up its rotation. Wheeler estimates that the companion star must have had a mass similar to that of our own Sun in order to account for Betelgeuse's current rate of spin of about 15 kilometers per second. Now, if Betelgeuse did swallow a companion star, it's likely that the interaction between the two would have caused the supergiant to fling some matter out into space. The material would have been flung off Betelgeuse at a rate of about 10 kilometers per second. And this allowed the authors to roughly estimate exactly how far from Betelgeuse this matter should be today. And as it turns out, there are two shells of interacting material identified in infrared images which are sitting to one side beyond Betelgeuse. Now, this was originally thought to be part of a bow shock wave created as Betelgeuse's atmosphere pushes through the interstellar medium as it races across the galaxy. And while we've seen similar occurrences with other stars, no one really truly knows the origins of this material with any degree of certainty. It's all speculation based on other observations. Wheeler says there is evidence that Betelgeuse underwent some kind of commotion about 100,000 years ago when it first expanded into a red giant. And he believes the swallowed companion hypothesis could explain both Betelgeuse's rapid rotation and also this nearby material. You're listening to SpaceTime. I'm Stuart Gary. The PanSTARS project, the world's largest digital sky survey, has finally been released, providing details of over 3 billion stars, galaxies and other celestial objects. The new catalogue is based on 4 years of observations, covering some 3/4 of the visible sky. It was back in May 2010 that the first panoramic survey telescope and rapid response system, or PanSTARS Observatory, a 1.8-metre telescope on Maui, embarked on a digital map of the sky in the visible and near-infrared part of the electromagnetic spectrum. This was the first survey whose goal was to observe the sky very rapidly over and over again, looking for moving objects and transient or variable objects, including asteroids which could potentially threaten the Earth. The survey took approximately 4 years to complete, scanning the sky 12 times in 5 filters. This immense collection contained some 2 petabytes of data, the equivalent of some 40 million filing cabinets. All this information then had to be properly catalogued so astronomers and astrophysicists could access it quickly to exploit the data. Based on PanSTARS, scientists were able to measure distances, motions and special characteristics of nearly all nearby stars, as well as brown dwarfs and stellar remnants such as neutron stars and white dwarfs. The catalogue will expand the sensors of almost all objects in the solar neighbourhood up to about 300 light-years. PanSTARS will also allow a much better characterization for low-mass star formation in stellar clusters. And it's also gathered over 4 million stellar light curves. This will allow astronomers to identify Jupiter-like planets in close orbits around cool dwarf stars in order to constrain the fraction of such extrasolar planetary systems. PanSTARS mapped our home galaxy, the Milky Way, to a level of detail never previously achieved. For the first time, the survey provides a deep and global view of a significant fraction of the Milky Way plane and disk, an area usually avoided by surveys given the complexity of mapping these dense and dusty regions. PanSTARS has also monitored our nearest big neighbour, M31, the Andromeda Galaxy. There, it detected several microlensing events and many new Cepheid variable stars. Cepheid variables are stars which pulsate at a given rate based on their mass. Scientists can use these stars as standard candles to measure cosmic distances. As well as improving distance accuracy to Andromeda, it's also allowed scientists to better constrain compact dark matter. Beyond our cosmic neighbourhood, PanSTAR's unique combination of imaging depth, area and colours has allowed it to discover the majority of the most distantly known quasars, some of the earliest examples of supermassive black holes feeding at the centres of distant galaxies. The rollout of the PanSTARS data is being done in 2 stages. This initial release is of the static sky, which is the average for each individual epoch. For every object, there's an average value for its position, its brightness and its colours. And for galaxies, there's further information, such as their brightnesses for various aperture sizes and seeing conditions. And later in 2017, the second set of data will be released. This will provide information for each individual epoch and also allow people to access the individual images for each of the observation runs. The full database will include information on each of the individual snapshots that PanSTARS took for a given region of the sky, consuming some 2 full petabytes of data. After that, scientists will begin measuring the redshifts or cosmic distances of different galaxies, as well as other cosmological objects. This information will help scientists analyze the distribution of galaxies in all three dimensions, basically piece by piece, building up an entire picture of the cosmic web, the structure of filaments connecting nodes and voids which make up the large-scale universe. This will allow astronomers to better infer the geometry of the universe, further constraining the standard cosmological model. And with the data for the individual epochs, astronomers can then even study variability in faraway active galaxies. I'm Stuart Gary. This is SpaceTime. 2016 has been an amazing year for astronomy and space exploration. There's been confirmation of the first ever detection of gravitational waves from colliding black holes. There's strong evidence supporting the possible existence of a ninth planet in our solar system, and we've seen the first successful vertical landing at sea of the core stage of a SpaceX Falcon 9 rocket. And 2017 will undoubtedly bring more highlights. Dr. Nick Lom is the Consultant Curator of Astronomy at the Powerhouse Museum Sydney Observatory. He's also the author of the 2017 Australasian Sky Guide, which highlights the major astronomical events for the upcoming year.
There is a partial eclipse of the moon that's happening in August, when 25% of the moon will be inside the Earth's shadow, and that's quite a substantial amount, and it will last for quite some time. It will last for almost 2 hours, so it's really worthwhile.
And will that be visible all over Australia?
Yes, it will. It's all over Australia and New Zealand as well, but it does mean for people in Australia getting up in the early morning. In Sydney, it begins just after 3 a.m. in the morning, so it does mean an early morning rise, but I think it's only worthwhile doing so.
August is an interesting month, isn't it? Because as well as the partial lunar eclipse down under, we also have a total solar eclipse for our listeners in North America, across the United States.
That's right. That will be a very spectacular eclipse because the eclipse track cuts across most of the United States, a very large part of the United States. And that's happening on exactly 2 weeks after the partial eclipse visible from Australia, which is fairly obvious because eclipses of the moon happen at the phase of full moon and eclipses of the sun happen at a phase of new moon. So that's 2 weeks later.
Other than just lunar phases, are they usually linked in terms of if we get a solar eclipse 1 week and 2 weeks later there will be a lunar eclipse simply because of the position of the moon in its orbit around the Earth?
It does happen quite often. So there's certainly a good chance if there is a total eclipse or there is an eclipse of the sun that there could be an eclipse of the moon 2 weeks later, or vice versa. If there's an eclipse of the moon, 2 weeks later there could be an eclipse of the sun. So they are very closely linked, but it's not a given, so it does not always happen. Other events in 2017, it's a very good year to look at meteor showers. The two main ones that we can see are in May, the Eta-Aquarid meteor shower, which is the one associated with Halley's Comet. The gibbous moon will set in the morning, sort of long before sunrise, so there'll be a good period, a good window of opportunity to see the shower. Similarly, the next meteor shower, the one near the end of the year, the Gemini meteor shower, which is the other sort of major meteor shower for the year, there is a crescent moon in the sky, so again, that's not going to brighten the sky very much, and there'll be a good chance to see the shower and the associated meteors.
The Geminids are always fascinating, aren't they? If for no other reason, simply because of how they're formed. It's not like most other meteor showers.
But that's right. They're associated with an asteroid instead of comet. I mean, every other meteor shower is associated with a comet, but the Geminids are associated with an asteroid called 3200 Phaeton, Phaeton, and this is an interesting asteroid. It approaches the sun closer than any other asteroid that has a name. It approaches to it in 21 million kilometers. And it's referred to sometimes as a rock comet because even though it doesn't have the gas or the vapor that's associated with comets, but bits of rock fall off it, and that gives rise to the stream around its pass around the sun, and that gives rise to meteor shower that we see every year in December.
Yeah, I think temperatures on the surface there get up to around 750 C, so really hot, and literally it causes rocks on the surface to crack, and occasionally those rocks get flung into space then. The spacecraft have measured notable amounts of dust coming off this rock comet on several occasions.
That's right. And then over time, that dust and bits of rock spread around its path around the sun. And then when the Earth happens to hit that path, which is in the middle of December each year, that's when we have a chance of seeing the meteors. And as I said, how well we can see the meteors depends on the phase of the moon. And fortunately this year, both for the Eta Aquariids and the Geminids, there's a time when the sky will be fairly dark, not lit up by the moon, and we have a good chance to see what the meteors flying through the sky. Other events during the year, there'll be opportunities to see the outer planets, Uranus and Neptune. With binoculars, we can find them with binoculars, but the reason they're hard to find with binoculars is because it's hard to know where to look. But both in January, Venus will be passing by Neptune, the outer planet Neptune, and in February it will be passing past the outer planet Uranus. And Venus will be close enough that it will act as a signpost. So with binoculars, we'll be able to easily find Neptune in January and Uranus in February. And that's something very few people have seen with binoculars. And so it's a very good opportunity.
Now, of course, all this is contained in the latest issue of the Australasian Sky Guide. It's a publication you bring out, well, you and the Powerhouse Museum Sydney Observatory bring out every year. And the 2017 issue is now available. And it's got pretty well everything you'd really want to know about what to look for in the night skies, especially from an Australian point of view. Most of the other sky guides that we see around the place, and there are lots of them, both online and stuff you can purchase, but because most of the people in the world live in the Northern Hemisphere, they deal a lot with that. So having an Australasian one, which looks at the Southern Hemisphere, is pretty cool.
Well, that's right. And it's very useful this time of the year because a lot of people go away on holidays and they have an opportunity to spend a bit of time outdoors and hopefully in a dark area and look up at the sky. And there are maps there in the Sky Guide every month showing where to look in the sky and what to see.
Are the maps difficult to understand and read?
The whole idea is to make them as simple and easy to read as possible. They're full sky maps, so it shows the brightest stars. So it's only the brightest stars are visible are on there, what you can easily see by eye, even from a city. The trick is that it's marked around the edges with cardinal directions, north, south, east and west. And the trick is when you're looking, say, south, you have it so that south is at the bottom of the map. If you're facing north, you have to have the book upside down, and then that will match what you see in the sky. Facing east, then you turn the book sideways, and that will match what you see looking towards the east. And there are times given for every month. There are particular dates and times given every month when it's most appropriate to use the star maps. It shows both the major constellations, major stars, but also the planets. And that's something that you cannot do without an annual publication because the planets move across the sky throughout the year. So it actually shows you where to look.
And if people want to get a copy of the Sky Guide, how do they do that?
Well, it's available from Sydney Observatory. It's available from Museum of Applied Arts and Sciences. It's available online from lots of bookstores. And it's also possible to download electronically. It's available from Amazon for Kindle. It's available from iBooks for iPhones and iPads, and from Google Play for people with Android phones and Android tablets.
That's Dr. Nick Lom, the Consultant Curator of Astronomy at the Powerhouse Museum Sydney Observatory. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter and Tumblr. Just search for SpaceTime with Stuart Gary.